On this episode of This Week in Space, we're talking about the rescue of Voyager 1. Stay with us.
Podcasts you love.
From people you trust.
This is Twit.
This is This Week in Space, episode number 110, recorded on May 10th, 2024. The rescue of Voyager 1. Hello, everybody, and welcome to another episode of This Week in Space, your favorite space podcast, the Saving Voyager edition. I'm Rod Pyle, editor-in-chief of Ad Magazine. I'm here, as always, with the ineffable Tarek Malik. Did I just say Tarek Malik? Tarek Malik.
Tarek.
It's because we were just talking about names.
Tarek.
The ineffable editor-in-chief of space.com. How are you, sir?
I'm doing well. I'm doing Road. I'll call you Road. Piali, right?
Just don't call me what one of my father's friends from the LA Philharmonic used to call me. For some reason, he decided my nickname should be Roddle Horse.
Roddle Horse.
I have no idea where that came from.
Because that's so much shorter than Rod.
I despised him on sight from there on out. Today, we're going to be joined by Linda Spilker, Dr. Linda Spilker, who's a JPL fellow, a senior research scientist and planetary scientist at NASA's Jet Propulsion Laboratory, and who is the second only project scientist for the Voyager mission after Ed Stone, who did it for 5 decades and was also central. She worked on Voyager when it was new and also was the principal scientist on the Cassini Saturn orbiter. So she's going to be a real pleasure to talk to. But before we begin, I have to remind you, don't forget, do us a solid, make sure to subscribe to this podcast so you can hear our dulcet tones every week, and like us and click all those buttons to make sure that the algorithms know that we're the cat's meow, because we're the cat's meow. We're counting.
Meow.
And now a space joke from Tucker Drake. A repeat visit from Tucker Drake. Hey, Tarek.
Yes, Rod.
Why does NASA still use liquid hydrogen as a rocket fuel?
I don't know why.
Because there's no fuel like an old fuel. Oh, that 1950s laugh track. Please save us from yourselves or ourselves or somebody's selves and send us your best work or most indifferent space joke at twis@twit.tv. That's TWIS at twit.tv. And actually, we've been running a pretty good inventory of jokes, but every now and then I have to resort to doing them myself. And that isn't something that any of you want. So do send them in as you think of them. All right. Let's do some headlines.
Headlines.
Boeing.
Big update. Big update on Boeing Starliner, Rod. Big.
Oh, I'm sorry.
Big
you woke
breaking
me up.
news.
Wait, what?
It's delayed again because of valves. No.
Well, and in this case, though, now this was interesting. So before... Wow. Before, we're flying these things without crews. So the valves were stuck and wouldn't open reliably. And 13 of them, some percentage of those. So that was a problem. This time they said had the flight not had astronauts on it, they would have proceeded, but they had a buzzing valve, which sounds like it was stuck in a partially open position. Is that what you understand?
That's right. And this isn't a valve. This isn't a valve that, how did that sound, Rod? Do it again.
I'm a buzzing valve. Hear me.
No, the valve is actually not on the Starliner spacecraft at all. So this is not a Boeing issue. This is not a Starliner issue at all. And
it's on the booster?
It's on the Atlas V rocket built by United Launch Alliance. And of course, so this story is from space.com, but everyone else is all the regular players are covering it too. But during the countdown, shortly before, they were getting close to the launch, about an hour or two ahead of launch, they the folks at Atlas at ULA started detecting vibrations in a different subsystem that they have seen before, and it's a vibration that is caused by what they call it a buzzing valve. It's a valve that is opening and closing so fast that it makes like a buzzing type vibration that they can pick up in some of the other accelerometers or sensors that are on the rocket itself. And this is a valve that is it's a pressure relief valve on the upper stage, the Centaur stage. It's a liquid oxygen system. So it's just a relief valve so it doesn't get too pressurized. And it's really important, and they want to make sure that it works all right. And if it was any other mission, because ULA had seen this exact issue before and similar types of valve issues in the past. If it was any other mission, like if they were launching a spy satellite or a commercial satellite, they would just flip a switch and cycle the valve so that it would open and shut, and then see if that fixed it. And then if it did, hooray. And that's what they have done every time they've seen this issue in the past. However, because there are astronauts on board Starliner at the time, Butch Wilmore, Sonny Williams, on board the spacecraft already waiting to lift off, they have these very specific flight rules at United Launch Alliance and Boeing and NASA that says you cannot change the state of the vehicle while the astronauts are on board. And that is like the key phrase. If they're going to cycle the valve open and shut, they're changing the state of the vehicle just to do that one thing. Even though they think it would be fine, their flight rules say they can't do that. And so because of that, they have to scrub the launch, which is kind of a little bit frustrating because an hour or two after the launch scrub, the buzzing was gone after the astronauts got off because they cycled the valve and it stopped, right? But this is the first time that they're launching people on board. So they're going to dot all their I's. They're going to cross all their T's. And so, if it hadn't been for those flight rules, then they wouldn't have done that. But they want to make sure that this is the first crewed flight of a brand new spacecraft. They want to make sure that they follow all of those things to the letter because there are reasons to have those flight rules in place. You don't want to change. So, you don't want to make exceptions every time because that's how you get into slippery slopes. So
not to belabor the story too much, but so on the one hand they say, we would have gone if it weren't for the astronauts for being extra careful. But then for whatever reason, they decided to or had to roll the rocket back in the barn instead of leaving it on the pad, right? Yeah.
And this is actually a really good point because buzzing, that rapidly opening and shutting, that suggests a really fast cycle for this valve. And the valves are only rated for a certain number of cycles, right? Of opening and shutting. And it's something on the order of, I think it's either 20,000 or 200,000. It's one of those two. I think it's 200,000, but they weren't sure exactly how fast it was opening and shutting and how many times it had cycled. And that's what they wanted to double check. Like if it's close to the maximum life, which was I think about 180,000 times, then they would have some margin, before the next launch. But if it had been going on for quite some time, it could have crossed that margin and then been a suspect valve. So what do you want to do? Do you want to replace the valve or not? And so they decided to replace the valve just to be safe because they did some reviews and they thought maybe it's at the end of its design life. And it takes them some time. So they rolled it back into their VIF, their Vehicle Integration Facility at Cape Canaveral Space Force Station. They're going to replace the valve and it's going to take them a few days to do that. And their next launch try will be May 10th. No, pardon me. May 10th was this week. May 17th.
Or after.
Yeah. May 17th or after. Yeah. And so it'll be, it could be the next time that you and I meet, they could be counting down again to launch the rocket if they think that they're ready for that. So.
Okay, well, then I won't make any more nasty Boeing comments since it was a rocket problem. All right, next story also from space.com. James Webb Space Telescope gets a weather report from exoplanet. And I'll just set this up by saying this blows my mind. 280 light years from Earth, we're getting an indication of not just atmospheric components, which they've done before, but actual indications of weather patterns. And all these kinds of things are at this point still kind of Sherlock Holmesian, mostly indirect. It takes a lot of intuition. You have to make certain deductive assumptions. And in this case, if I have the story right, this measurement is done by comparing the spectra of the star it's circling to the spectra of the star when the planet is illuminated by that star off to the side, and then subtracting out the differential gives you some kind of weather, but also the shift that you're getting of that spectra is what's telling you what kind of weather you're getting. Is that right?
Yeah, this is an interesting one, and I think you mentioned 280 light years, but actually this one, that if we're on the same story, it's 55 Cancri E, which is 41 light years.
Oh no, I was talking about a whole nother star. Okay,
yeah,
but same idea.
Yeah, well, this one is interesting because 55 Cancri E is not like a new exoplanet, but it is one that NASA and scientists have known have had an atmosphere for quite some time. In fact, when I first wrote about it, and this is many years ago, more than I would like to count, it was described as like
Crimea River, baby.
It was described as like a cotton candy planet or a puffy planet because it had this real kind of puffed up atmosphere around it. And this is where they were studying it with kind of some older space telescopes. The study that we're talking about is new because they used the James Webb Space Telescope to do it.
Right.
And so 55 Cancri E, because it has that E in its name, it's apparently it has a nickname called Johnson. I'm not sure how you pronounce that. It has 2 S's, 2 N's, a J. I respect the J, but it's one of 5 planets around the 55 Cancri star, which is much like the sun, and it's in the constellation Cancer. And the diameter, it's about twice the size of Earth, and it's a bit denser than our planet. So they think that it's more like a super Earth. It's larger than Earth, but smaller than Neptune. And they think that its composition is very rocky, but it had this atmosphere that they thought that it disappeared. It was really puffy. But it's so close to the sun that the star could blow off the atmosphere. It's about 1.4 million miles away from the star. That's like super close, much closer than Mercury is to our sun. And so that the surface was probably super molten, like a big old lava ocean world. And in a stunning discovery with James Webb,
stunning.
They found that the atmosphere is back, that it came back. Basically, they watched as it dwindled away. They thought it got burned up by the star, and James Webb has found that it's grown back. And that is like the big wow moment, that something is happening on this planet to revitalize its atmosphere and keep it going. And I think it's just perplexing. This strange planet, this puffy planet, got stripped of its atmosphere, grew it back, and there's other stuff happening on it that it's making it a very tantalizing target. Very weird planet for sure.
Making a very saucy story. All right, and as our third and final story, you just can't have a week go by without something happening with our pal Elon Musk. So Elon has decided that he understands the question of aliens. Yes. Not
the question of it, but at least he's kind of given his stance on it. So this week we were surprised actually to find out that Elon Musk, a SpaceX founder and CEO, he was talking in a panel at the 2024 Milken Institute Global Conference in Los Angeles, Rod. So around the corner from you.
Yep.
On Tuesday, and he was asked, like how he felt about new life and new forms of civilization. Are there aliens out there or not? And he actually mentioned, during that talk that if we send probes, we might be able to find those remains of long dead alien civilizations out there. But he did say that he didn't feel that aliens have like visited us, to, I don't know, go cow tipping or abduct, the people out, from their beds. Yeah, I wasn't gonna say hayseeds. I almost said bumpkins, but I wasn't gonna say it. I almost.
Well, it's a long way to drive to grab people and do cavity searches after you've done a couple 100,000 of them. It's like, come on.
Exactly. Like one or two, okay, but 20 years on. But what he said, and I quote, he says, "I don't see any evidence of aliens." And why would that matter coming from anyone? Well, here is Elon Musk with SpaceX. It's a company that has like 6,000 Starlinks active in orbit, and he says SpaceX has roughly 6,000 satellites, and not once have they ever had to maneuver around a UFO. I mean, that's pretty compelling, right? There's a lot of space junk up there, but you would think that if there was a lot of alien traffic, they would have figured out something. Now, the aliens obviously could be very technically sophisticated. They could have cloaking devices like the Romulans and the Klingons. We don't know.
The answer is much easier than that. He is an alien. We all know he's an alien.
Oh, he's in it. Is that what you're saying?
He's in on the deal, and he's trying to hide the fact that they've taken over all levels of government, and that makes it very simple. And, I'm going to get quoted on this, and that'll be a bad moment for all of us. All right, let's get a piece of fan mail read here.
Yes.
Then we'll move on to our interview. So Tucker Drake, who has a podcast of his own, writes about our music and space episode. I'm glad the episode talked about how music helps us express things that we can't always put into words, and emphasized that it also helps us understand things we might not otherwise be able to. He talks about all the great science we got from the lunar missions and so forth. But I think the part that compelled me the most was the second paragraph, which is the one thing I wish someone would have mentioned in the episode. And I'll lay this failure at your feet, Tarek, since you're the only person besides me that's here, would have mentioned the episode was that had Challenger launched in warmer weather on that fateful day, Ron McNair would have performed the first music to be recorded in space. I didn't know this.
No,
he brought his saxophone with him and was supposed to play a part that would have been used on a Jean-Michel Jarre album entitled Rendezvous. Jarre, who's the son of film composer Maurice Jarre, did eventually release the album with the sax part played by someone else on Earth and dedicated it to the crew Challenger. And I had no idea that Ron McNair even played saxophone.
That's amazing.
Flying one.
Wow. And very appropriate for our music episode. So
yeah,
thank you, Tucker. So
and it's interesting because that reminds you of those heady pre-Challenger days where the shuttle was seemingly becoming kind of routine, and they were going to launch teachers, they were going to launch journalists, anything goes. It's our truck to space and all that. And then we had that horrible wake up call and got a dose of reality about what was really going on with the space shuttle, which ended up being much more fragile and challenging than we thought. What were you going to say?
I was just going to say, thinking about our music in space. I mean, that's very, very kind, or very good words there too, Rod. I must commend you. But speaking of our music in space episode, I actually saw Chris Carberry, our guest, in person this week in Washington, D.C., because as we alluded to last episode, he and the Explore Mars organization put on the Humans to Mars conference, and I was there, gratefully at their request to moderate a panel about how AI could help us explore Mars and get humans to Mars. But it was a fascinating conference with many different talks. Jim Green was there talking about a single launch that could get us a Mars sample return mission, and much more streamlined than what we've got planned right now. So it was very exciting. But there were many other concepts, and maybe we can go into that in a future episode. It was really enlightening stuff. Very great conference if you're ever interested. And I think you can go to the Explore Mars YouTube and watch the full conference now too.
Yeah, they usually record it. Yeah. And speaking of Mars, we will have, if plans continue to go as they are planned, we will have Rob Manning, who is now the Chief Engineer Emeritus from Jet Propulsion Laboratory, on next week to talk about the future of Mars exploration, ? But before that, it's time for us to meet Linda Spilker. So stand by. We're welcoming Linda Spilker to the show. Thank you very much for joining us today. It's a real pleasure to have you here.
It's a pleasure to be here, Rod.
So can you give us just kind of a capsule summary of your career? Because I met you, I guess, during the last couple of years at Cassini, and I was there for the last moments, which were pretty teary for me. I think it was
pretty emotional. Yeah.
And almost more compelling because we weren't looking at visuals. We were just seeing that signal, that little radio spike slowly go down. And when it flatlined, oh my God, it was like,
right. Yeah. Good word for it, flatlined. And that was the end of Cassini.
It was like spaceship hospice. But anyway, moving on to happier things. Can you just give us kind of a rundown of your career track?
Okay. I started at JPL in 1977. It was my first job out of college, and coincidentally, it was the same year that Voyager launched. I was given the opportunity to work either on Voyager or Viking, and I thought, well, Voyager is going to visit places I've always been interested in and wondered about. And so I said, sign me up for Voyager. And so I got to go to the launch and was part of the 4 planetary flybys, Jupiter, Saturn, Uranus, and Neptune. And also during that time, we're part of a couple of science teams, worked with the infrared team and also with the photopolarimeter team. and used some of the data from Voyager for my PhD thesis. So I wrote my thesis on the rings of Saturn, Uranus, and a little bit about Neptune's rings too. And then along came this opportunity after the Neptune flyby of a new mission that ultimately became called Cassini. And Cassini was headed back to the Saturn system. And of course, Saturn has the best rings in the solar system. So that was easy. I said, okay, I'd really like to work on this mission, and went over and spent the next almost 3 decades working on Cassini from the very beginning as a mission concept through the end of the mission. And after the mission ended, we wrapped up all the paperwork for NASA. There was an opportunity to go back to Voyager. I had a chance to work with then project scientist Ed Stone. He'd been working on Voyager for 50 years from the very start of that mission. And so I worked with him as his deputy, and I was just so much in awe of him through the planetary phases. And to work with him again was a real pleasure. And so then when he retired, I became Voyager project scientist, and I'm thrilled to be back where I started my career.
That's great. And of course, Linda, you were the one running that fort when we had all the recent problems. I mean, Voyager 1, the reason that we'd called to kind of see how things are going was because of the triumph over some adversity that you and the team had to go through over the last 5-6 months, over the last half year. I'm just curious how large the team is now, and what sort of science now, 46 years later, Voyager 1 is still doing.
Right. Well, the flight team on Voyager these days is quite small. It's maybe about 12 people. Most of them are part-time. They're spending their time on Voyager and another mission, perhaps like Psyche or some of the Mars missions. And then the science team, we're down to 5 instruments still operating on Voyager 2, 4 on Voyager 1. And those teams are also quite small. But there are many of the original people who were there when Voyager launched, or even before, were part of both the flight team and the science team. So it's a real tribute to Voyager, the longevity, not only of the spacecraft, but of the people on the team as well. As far as the science goes, we've crossed this boundary called the heliopause. The sun controls its own sphere of influence with the solar wind, regulated every 11 years. You can imagine this bubble kind of breathing out, in with the solar cycle, pushing back against the interstellar wind. And so Voyager 1 crossed this boundary in 2012. Voyager 2 crossed it in 2018. And since that time, we were the first spacecraft ever to make direct measurements of the interstellar medium. Things such as, what's the cosmic ray abundance? What's the abundance? What's the composition of the cosmic rays out there? Because the heliopause is a very good shield. Shields us from about 70% of the cosmic rays. Then, of course, what about the interstellar magnetic field? That's one of the puzzles still with Voyager. Once we crossed and left the sun's sphere of influence, we thought the magnetic field direction would rotate into the interstellar direction. And that hasn't happened yet for either Voyager spacecraft. We're still waiting. And so we don't know if we're kind of in this intermediate region. We're also looking at, when does the sun's influence die out? We still see effects from the sun, some of the big events, coronal mass ejections that send out particles that actually have signatures as shocks or pressure fronts in the interstellar medium. And so we still see those. So where does the sun's influence end? And then, of course, what we're measuring is the environment around the spacecraft, the plasma, those charged particles, not only electrons and protons, but of course, there's a lot of helium and hydrogen and other things in the interstellar medium. And you ask, well, what creates the interstellar medium? It's created from supernova explosions. These large stars at the end of their life kind of implode and then explode and send all their material and other things that they've created out into interstellar space. And so we're in a bubble right now called the local interstellar cloud. And so we're measuring the plasma and the properties of the local interstellar cloud.
That's so wild. You're like in the space between space out there in our cosmic neighborhood.
I like that, cosmic neighborhood. That's where we are.
So I talk about this on the show often, but since we have you here, I just want to comment for our listeners. I only visited Voyager Control once when it was still off lab in that little office down the street. but was struck with how efficient it is. So, I mean, you're still, at the time anyway, they were still using a couple of old workstations that I guess dated most of the way back to the original launch of the flight, very old computers. Oh, well, a little later than that, but they were little workstations on a banquet table, as I recall, and just a handful of people. And it's incredibly efficient. And I think it's important people understand this is not an expensive mission to run anymore. This isn't one of those billion-dollar flagship missions we hear about. This is just pennies on the dollar compared to almost anything else to keep this thing going and for all this
absolutely right
getting back.
Yeah.
And also, people talk a lot about, Voyager's left the solar system, and it kind of has, but it hasn't left the Oort cloud. And I wonder if you could sort of explain what the difference is between the heliopause, the boundary that you have crossed, and the greater solar system neighborhood that we're in now.
Right. Well, the sun's sphere of influence for the solar wind stops at the heliopause, but its gravitational influence extends out much, much beyond that into what's the Oort cloud, that spherical cloud where we get a lot of our comets and those other objects that are controlled by the sun's gravity. So if you go out all the way out to the Oort cloud, that's much, much bigger than just crossing the heliopause. You're absolutely right.
Linda, for some of our listeners, who may not be aware. I mean, Voyager 1 and Voyager 2, of course, and I think it's always funny that Voyager 2 launched first ahead of Voyager 1. They may not recall kind of the ambitious nature of the Voyager mission, what was accomplished. To them, Voyager has just been always out on the farthest reaches, the farthest human-built object in space, but it had this huge solar system tour that swung by so many different planets. And I'm curious if you could help our listeners understand the sheer ambition that the Voyagers were and how these were like our first up close looks at Jupiter, at Saturn, at Uranus, at Neptune. In history, I think a lot of us take that for granted now that we have all of these great photos. I mean, I have a whole suite of posters that I got from the education office at JPL that are massive movie poster size images that were taken by these spacecraft, when I was just a few years old, basically, in the 80s, not a few years old, I was like 10 or whatever, because I was watching them come in during the rendezvous themselves. But can you kind of touch on just kind of putting that together? Hey, here's an alignment. We launched these spacecraft in 1977. We're going to be able to hit not one or two, but 4 planets in all, if we can time it just right and get the trajectories. So just the scope of that mission there and what it meant to you as a scientist to be able to get all of that together.
Oh, absolutely. I'd be happy to share about that. Well, JPL started building the 2 Voyager spacecraft in 1972. And for context, that was only 3 years after we had the first human walk on the moon. Wow. And the reason we started that early is that you're right, we had this rare alignment of the planets. Once every 176 years, with a single spacecraft, you can visit Jupiter, Saturn, Uranus, and Neptune. You fly close to each planet and you use the planet's gravity to curve your trajectory to slingshot you around out to the next planet. And it's notable that the funding for Voyager originally was for 4 years. And that would have included 2 flybys of Jupiter and 2 flybys of Saturn, because that was what was in the NASA budget at the time. And after the second Saturn flyby, and both spacecraft are still healthy, still working, Voyager 1 was finished with the planetary flybys. It flew close to Saturn's moon Titan, and that bent it up out of the ecliptic plane. But we targeted Voyager 2 at Saturn to continue on to Uranus and Neptune. So NASA said, go for it. Hey, you got healthy spacecraft, go for it. So we did. And that led us to be the first spacecraft to visit Uranus and Neptune. And that's still true to this day.
Wow.
Although NASA does have, as part of its plan for the next planetary flagship, to launch something called Uranus Orbiter with Probe, to take a Cassini-like spacecraft and orbit Uranus and study that system, an ice giant, in detail. So I'm very, very excited about that mission. Tremendous discoveries in that phase. In particular, what really strikes me is what we discovered about the moons. In a telescope, these planets are huge. So you get a pretty nice view of the planets. But the moons, especially some of the smaller moons, are just points of light. So one of the things that Voyager gave us was to get close-up views of these moons so that they became worlds in their own right. We found volcanoes on Io at Jupiter, a bright icy world for Europa. At Saturn, of course, seeing the rings and all their glory and detail. Just incredible, just spellbinding to watch those pictures come back. Tiny Enceladus, that's bright white and icy. And so, in a sense, Voyager left the breadcrumbs of what future missions could follow up on and help with the design of their instruments. A good example is Cassini. Voyager 1's goal was to fly close to Titan and to try and get a view of its surface. But as we know, the Voyager cameras and the instruments didn't have the filters and the wavelengths they needed to penetrate through that thick photochemical haze. Titan's atmosphere mostly nitrogen, the methane's broken apart by sunlight, creating essentially a fog, or a smog, creates a smog around Titan. So that led to a plan almost immediately for a mission like Cassini to carry a probe provided by ESA to parachute to the surface of Titan. So that was just one example of a breadcrumb. Europa Clipper that will launch soon is following on not only on what Voyager first discovered about Europa, but also Galileo. And so just sort of, you can see these other missions sort of standing on the shoulders of Voyager. And expanding out in what Voyager learned about. And then, of course, there's this whole heliosphere that Voyager was the first spacecraft to sample and go all the way to the outside, and now interstellar space. So Voyager keeps reinventing itself as a new mission and at a very good budget cost, too. You don't have to build a new flagship to get all the way out to interstellar space. You've got something there now with very capable instruments to make measurements of a place we've never been before.
So your mention of breadcrumbs has inspired me, and I've got a question about that, which I'll ask as soon as we come back from this break, so go nowhere. Okay, so I have a question about breadcrumbs. So the Pioneer 10 and 11 probes, which were much smaller and less ambitious, but still ambitious for their time, if I remember right, launched in the early 70s, 72, 73 range, was what came, and the pictures that came back were great, but they weren't really, those probes weren't designed to do good visualizations, as I understand it, or image capture. That was kind of a nice side effect. But was that inspiring to you when you got into the Voyager program from what you had seen from Pioneer?
Well, the Pioneer data were very useful. In fact, it was Pioneer's flyby of Jupiter that really told us just how harsh the radiation environment was at Jupiter. And it was at enough time to allow us to provide extra shielding on the spacecraft to protect against that radiation. Voyager 1 went into 5RJ, which is, really a very intense radiation. And Voyager 2 is a little bit further out because it was setting up for basically the grand tour of all of the planets. But that helped us in another way. Now that we're out in interstellar space and the cosmic ray abundance has jumped up, that's basically radiation. And so having that extra shielding, for the computers, for the parts of the spacecraft, we actually used that lesson from Pioneer. But it was inspiring and tantalizing because you just got hints of perhaps what might be new rings and looking at some of the data about Saturn. And it was very tantalizing, and it just made the excitement that much greater, a chance to go back and really, with a good, capable camera at the time, it was just a Vidicon camera, and look at these worlds and look at the moons.
So your comment about the radiation environment reminded me of a story. I wrote a book about JPL interplanetary missions a few years ago, and I had a couple of long interviews with John Cassani, who told the story about how late in the game, as they were building this thing, designing it, they realized that beyond radiation, there's also going to be a harsh static environment, I guess. And I said, well, how did you solve the problem? And he kind of did one of those and said, I sent somebody down to the market to buy some Reynolds wrap, and we wrapped the cables in aluminum foil. And I thought, boy, that has got to be the most cost-effective solution NASA never came up with, is the $3 roll of Reynolds wrap.
That's expensive for the 70s.
Well, that's true. It was probably more like 50 cents when I think about it. So the pioneers faded out before they left the solar system, correct?
That's correct. They didn't cross the heliopause. In fact, we didn't know where the heliopause was until Voyager actually crossed it. There were ideas, models, theories, but didn't know until we physically crossed it.
So you've kind of explained this, but for the layman here, including both of us, in broad terms, what really are the principal differences between being, quote, in the solar system and, quote, out of the solar system beyond the heliosphere?
When you're inside the heliosphere, you're in an environment where there's a lot more particles from the solar wind. And so that you can actually make measurements about those. You see lots of effects from the sun. Coronal mass ejections go all the way out to the edge of the solar system. And so you can study those effects, the interactions with the planets. There's different regimes, the heliosheath, kind of different regimes you cross through and can study and understand more about this environment around our sun and just how much it's basically in some ways protecting the planets in our solar system and giving us clues about what these heliospheres, we call them asthenospheres, might be like around other stars as well. And in some cases, if there's a lot of gas and dust around, we can actually see some of these, and they're quite extensive, like our suns.
So what's really happening at that boundary we're talking about, if I understand correctly, is the energy coming from our sun meets basically a pressure point with what's coming from the galaxy itself, from cosmic sources. And that's kind of what, I guess, contains what you're talking about, like coronal mass ejection particles and so forth. Is that right?
That's right. That's right. And in fact, this whole structure, the heliosphere, is actually moving through space. So it has a nose, and it's just fortuitous that both Voyager spacecraft are headed in the direction of the nose. We're not sure about the shape of the tail. There are theories all the way from the heliosphere as a bubble, spherical bubble, to sort of a comet-like long tail, to a croissant with maybe kind of two tails, two parts of a tail. So there are lots of ideas about what the tail looks like. And we're just lucky that we headed toward the nose, which is sort of the fastest way to cross the heliopause.
We live in a cosmic croissant. I like it. Lynn. I wanted just to ask about the design of the Voyagers, because it is very singular, in terms of people can see it and they're like, that's a Voyager spacecraft. You have the big 12-foot dish, the big boom on the end, and so that it just looks otherworldly. And now, of course, I guess other solar system-y. I'm not sure how interstellarly. Yeah, and it's carrying in addition to the instrument suite, the golden records that are on those vehicles themselves that have like the sounds of space, and it just sounds like it was designed more for just exploration, but as a bit of a vehicle for humanity as well. So we're going to go learn about these planets, learn about the interstellar medium. I won't say void because obviously there's particles there that you're detecting, but it's also a bit of a messenger in its own right. And I'm curious if that was always discussed when in those early days when you were planning everything out during the mission that you expected it to kind of be that dual purpose there.
Well, we knew from the trajectories that both Voyagers would pick up enough energy, enough speed to leave the solar system and not come back. Mm-hmm. And so part of the purpose of the golden records is, with the sights and sounds of Earth, the music, Johnny B. Good on, Chuck Berry's music on it, that they were carrying these records, and there's on the cover a way to go back and find us using some of the local quasars. If you look at this diagram and can interpret it, you'll find us a picture of a man and a woman next to the spacecraft to give an idea of our size. And so when the Voyagers run out of power, probably sometime in the 2030s, barring any other hardware problems, then they become what we call our silent ambassadors. Each one headed out towards other stars. We have actually trajectories out about 1 million years from now, knowing what stars we'll get relatively close to. And it will just be a question of whether there might be some other species that might find Voyager and come back and see what we're up to at that point in time.
Well, the 2030s isn't that far away. Oh, no.
All right. Well, we'll be back to talk a little bit more about that in just one moment. Stand by. Can I ask you a computer question?
Sure.
So we talked about the ground computers, but I'm continually fascinated, and I guess it started with the Mars rovers, realizing what kind of computers they were operating with. You're talking to a spacecraft that's 15 plus billion miles away that is running some chips, some custom fabricated chips built by Texas Instruments that were baselined. I mean, the original chip design was baselined in 1964 when, integrated circuits were barely even a thing then. And, to be able to continue talking to these things and using this very low bandwidth data recorder that's a tape drive, it's running tape back and forth over the same heads for 50 years. I guess the things that blow my mind are, A, they're still working in this radiation saturated environment. At least it was when they were out, doing the flybys. B, you've got magnetic tape that's running back and forth all these years that's still working. I don't have any magnetic tape that still works. And C, just, knowing how to program for and talk to these things that are so elderly. This must be a really difficult management problem for you planning your campaigns.
Well, the other thing that's important is that the Voyager computers are small, very small compared to what we think of as computers today. In fact, the memory in your key fob is more than what's in the Voyager memory. And
that's
so
a
that
great
means,
analogy.
Wait, you said key fob. So the thing that beeps the car open.
Right, opens your car. Yeah. And so you think about your cell phone, how much more capable with its camera, how much more capable that is. And so the programmers had to be very clever. And so they had to write subroutines that got called by multiple other routines on board the spacecraft. And so when Voyager 1 went through its anomaly, that was quite a challenge because there's actually a chip, 256 words that were, that was basically stuck bit. And so we had to take all of the subroutines in that portion and move them to another place in the memory that was good, and then relink all those subroutines and get everything that called them to work properly again. And so that was a challenge. But first, just finding out what was wrong with the spacecraft. Here, one day we have good science data, good engineering data coming back. The next day, all of a sudden, we just hear essentially a tone. It was sort of a repeating series of zeros and ones, but no information coming back. And so that's what you started with to try and fix Voyager 1. So you try some of the more obvious techniques. You start turning hardware on and off to see if something might reboot in a sense and come back. And then you notice that doesn't seem to help too much. And then you start poking a little bit, sending little commands into the hardware to see if you get a response. And slowly, bit by bit, worked our way up to getting a memory readout of the flight data subsystem. And in that memory readout, that's where we saw that one of the chips had failed. And then what I call the rescue mission began to sort of reprogram and send that code up. And Voyager doesn't have any physical hardware test beds. Often a mission, you can run your software, whatever you're going to do, through hardware on the ground that's very similar to what's in space. And Cassini made good use of that. Or sometimes it's software. You have software testing that you can do on it. But in the case of Voyager, the test beds are long gone. We don't have any software that we can use to run it through. So it was sort of an eyes only. I think 3 different people looked through the bits of code that they had written to put in another place of the memory to make sure it was correct. And then we sent it up.
So that was going to be my question. The amount of sweat that would be coming off my palms if I had to be the guy that pushed that button, because I'm old enough to remember when Viking 1 shut down because of an erroneous bit of programming that was checked before it went up, but we lost contact with it. So you're saying that there is not a physical 50-year-old test bed on the ground that you can run these things through first?
The test beds are long since broken. And there was always the feeling that Voyager's only going to last another couple of years. And so the question was, do you invest the time and the effort to keep your test beds up and running? And so they thought, no, it's okay. We can do without, the test beds. And
oh my gosh.
It's really a tribute to these very bright engineers. I remember going in and they had all of the circuit diagrams up on the wall and sticky notes all over the place. And one of them said, "This is just so fascinating. I've never done anything like this before." And he had to kind of trace and figure out what was going on. That was in the early days before we knew exactly what was wrong with Voyager. And you're right. The people that wrote that code, we all gathered on a Saturday early in the morning to wait for it. The other thing for Voyager 1 is it takes 22 and a half hours at the speed of light for a signal to go up to Voyager 1. And then we have to wait another 22 and a half hours, almost a light day each direction to get the information back. So here we are seated together watching for that signal to come back. I had brought in some Lucky Peanuts, and I think Lucky Peanuts that can always help. So we were passing around Lucky Peanuts and munching and just watching, as the minutes tick down for when everything should come back to life on Voyager, if this code worked correctly. You could have heard a pin drop in the room. It was very silent. Everybody's looking at the screen, waiting and watching. Everybody, the people that had certain subsystems they were responsible for had their screens all ready to see if the data would load and what it would look like. We needed sort of a health check on Voyager 1 because it had been 5 months since we'd had any information. And that minute hit, and all of a sudden it started to populate the data. And it looked, the program was working as planned. All of those changes were working. And so those programmers, they just jumped up and they cheered. And they were the happiest people in the room, I think. And there was just a sense of joy that we had Voyager 1 back and relief. It had been a long wait to see just what was happening again on Voyager 1.
That is fascinating. She just said that Voyagers themselves have outlasted their ground backups. That's how well they were built, and how nerve-wracking it must be to be one of those code reviewers. There's just 3 people on the ground to double check. Right,
at least 3. I mean, 3 key people responsible for just line by line going through, and it wasn't a lot of code. There aren't that many words in the Voyager memory, so it wasn't a lot of code they had to replace. And looking at it carefully and making sure that it would work. And it did. The key thing though, right now we're just getting back engineering data, which is important to make sure that, the attitude control system looks like it's doing well. The command and control subsystem, that they're all doing well. The power looks okay. So the spacecraft is basically healthy like it was in November. The next step over the next few weeks is to now send up a little bit more code that will give us the science data modes to send the science back. Mm-hmm. And so I'm really looking forward to that. There's a feature we were watching just before the anomaly. It's called nicknamed Pressure Front 2. And it'd be very interesting to see if it's there. We first saw it in the 2020s. It was a jump in the magnetic field and the plasma. And it continued over those, 3+ years. And it's so different from anything we've seen. Usually most events, shocks from the sun, go up, and then over the next few weeks or months go back down. So Pressure Front 2 is hanging in there. Is it a solar effect? Is it something coming from interstellar space, or a combination of the two? So it'll be really good to see if it's still there and see what it's doing.
Oh man, so this glitch came up and you were stuck on a cliffhanger of science.
That's right. Well, we've been watching it for a little over 3 years. But we'd really like to see if it's still there. And it doesn't represent a boundary or something different. Different about interstellar space.
So just, I guess really quickly, just for the timeline there, because I think we're going to go to a quick break after, but you mentioned this happened in November, this switch to just the tone, and then the investigation to try to solve it all. And is the 5 months there that it took to get there solely because of how difficult a trick it was, or is it really because of that light delay? You can only do one thing and then you have to wait. And when you wait, what's everyone doing for that 22 hours? I mean, I think I would be on pins and needles the whole time, but it sounds like you have to, move on and just wait for the answer and be patient, it seems.
We tended to command about once a week. And so you'd have that 2 days from when the command went up till you saw what had happened. And in the meantime, you were thinking ahead about what else you might try if it didn't work. And so in the beginning, we were careful and cautious about what we tried. And then as the series of things, we sort of had a decision tree. As you go down the paths of the tree, you just have to try more and more aggressive types of poking at the computer, or, you're looking through old memos to get information. It's like, an archaeological dig. Can we find a memo with an anomaly that was like this? Turned out in the 1980s, something very similar happened to the flight data subsystem. A chip failed, a hardware failure, and they had written a little piece of code all the way back in the 80s. So we had that piece of code, but we didn't have the nice documented version of the code. We basically had kind of the machine language code that we had to sort of translate back into human understandable code and use that as a starting point. But it was very useful to have that code that was written actually back in 1980 for Voyager 1 for a similar kind of anomaly.
So for some reason, my brain's still stuck on the idea of being that person that was working out this new bit of code to send up and put the comma in the wrong spot or something. The next thing you know, it's like, we didn't hear anything after hour 23. Like, oh my God. All right. We will be right back after this short break. Our last one. Stay with us. So at this point, have you figured out, it sounds like you did, exactly what happened up there? Was it a cosmic ray data hit or something, or an actual chip failure, you think?
It could have been a cosmic ray hit that caused the chip failure, or it could just be old hardware. We don't know what exactly caused it, but clearly it's a piece of hardware that has failed. Sometimes with a cosmic ray hit, we might flip a bit, and then we can go back in and put the right words into that memory location, the right values, and we're okay. But this was much bigger. It took out a lot of 256 words.
If I understand correctly, part of what makes this older hardware more radiation tolerant is just simply that it's larger, and that it was able to withstand more of the impact on those heavy ions than something modern would. Is that right?
That's a factor. You're right. All the components themselves are larger.
Just really quick, I mean, would that mean, if we have all these new fancy chips and boards that for the spacecraft that are being launched today, would they be as resilient in 46 years as the Voyagers have been, or are they more susceptible because they're more complicated and more, I guess, dense with the chips and stuff that are on them?
Yeah, those tiny chips are certainly more complicated. But along the way, I think we've learned a lot about how much shielding we need and what's the best kind of shielding. And for instance, Europa Clipper has a lot of there are a lot of components in what they call the vault, which is very heavily shielded because their orbits take them in to fly by Europa. They have to get close to Jupiter. So I think we've learned a lot about how to shield along the way and how thick and how much mass that shielding has to represent to do that kind of a job.
And for Voyager 1, because like you mentioned, the RTGs, their nuclear generators will eventually run down to a point where you won't be able to get a signal back. And you kind of mentioned that you expect that could happen in the 2030s coming up, which, man, that just doesn't seem like that far away. but if one goes out before the other, like because they're in different parts of, I guess that interstellar region, like what can they do together that you wouldn't be able to do if Voyager 1 goes out, or if Voyager 2 goes out, or can Voyager 2, because it is in a different place, fill in a lot of the other same types of gaps in science?
Yeah, well, actually, they're like having two unique explorers, and they're separated not only in space, they're actually further apart than Voyager 1 is from the sun. I think about 180 AU apart, and Voyager 1's 160 from the sun. Oh. So they can look at different spatial regions, and also there's a temporal difference. Voyager 2 is on a slightly slower trajectory, so it's not as far from the sun. It's like 13 billion miles, and Voyager 1 is 15. So sometimes effects we see first at Voyager 2, and then we'd like to see, do they propagate out to Voyager 1? So you have sort of a temporal difference. You can look at, what the effects from a different point in the solar cycle might be at the two different spacecraft. If you see a really exciting event, you could see, do we see it at Voyager 2 and Voyager 1, both the same kind of event? And for the sun's influence, as you can imagine, as our bubble of exploration expands outward, do we reach a point where the effects from the sun really become weaker and weaker? And then do we lose them at that same distance with Voyager 2? Or how uniform is that interstellar space that we're flying through?
So we have, I'm glad to hear you're thinking 2030s. Last I had read, people were talking about mission conclusions somewhere around 2025 or 26. Do you have an idea of the science that you want to try and do? Do you have a campaign plan for the remaining years that it's active?
Yeah, well, first I would add our sort of our shorter term goal is let's get to the 50th anniversary. that would be a great anniversary in 2027 to celebrate just how long the Voyager mission has lasted. And, starting in the mid 20s, we're going to have to start turning instruments off. We've basically turned off most of the redundant systems and the power systems that we can. And we're down to pretty soon, we're going to have to start turning off the instruments one by one. And so in the 2030s, we're hoping to have at least one, maybe two instruments still operating at that point in time. As far as the campaign, both Voyagers continue to make discoveries. There's more modeling that's going on. Longer term, to provide information for a future mission, like an interstellar probe, could we provide information that might influence the kinds of instruments they might want to fly, anything different they might want to do about their mission, just by continuing, to a few AU per year, keep moving out of the solar system. And like I say, we've seen Pressure Front 2. So are there any more surprises along the way? And will Voyager 2 also see the equivalent of a Pressure Front 2? Or is it something unique to the region that Voyager 1 is flying through? So having two spacecraft is like having two eyes looking in different directions, and we can compare what we see.
Yeah, don't we wish you could still launch twin missions? That was
absolutely.
Well,
yeah, my ideal planetary mission would be a pair of spacecraft. One goes to Uranus, one goes to Neptune, just like we did with Voyager, 2 orbiters, and send those. But it's a question of cost to be able to do something like that.
Mm-hmm.
So at this point, and I haven't followed the mission ending of everything, but I remember looking at most of the Mars missions, and other than errors like we had with Viking 1, in general, these things are turned off when the end comes. But we have this unique situation with Voyager where there's this increasingly tenuous little tiny signal way out there that you have to aim all these big Earth dishes at just to hear the whisper from 15 billion miles away. At a certain point, do you say, okay, it's time for mission conclusion and we're hitting the switch, or do you just let it fade out and continue to transmit?
If you ask the Voyager team and the Voyager scientists, the right answer is just to let it keep going until there's no longer sufficient power to basically continue to point the spacecraft at the Earth and control it. Because that, as that power runs out, then we're not going to be able to point the spacecraft. And at some point it might start to tumble, or it will be out in space. We won't be able to communicate with it. And it still could perhaps be there, but it won't be able to transmit back to our Earth. It's that very narrow, tiny little angle it has to hit to transmit to the Earth.
But it's still being oriented by gyros. There is still maneuvering fuel left?
What we're using is, we're not using gyros, we use thrusters. Little tiny thrusters, that puffs of gas that orient Voyager in each of its 3 axes. And one of the other challenges with Voyager is that the hydrazine, inside the hydrazine tank, there's the silicon bladder that has leached into the hydrazine, and that silica is plating out inside these very tiny, the opening to the very tiny thrusters, and clogging them up. So you kind of think of like maybe Voyager has a little bit of heart disease here, clogged arteries. And so it has to, so instead of 1 puff, it might take 5 or 6 puffs to keep it pointed. And so we're carefully watching. We've switched to all the backup systems that we've had for the thrusters. So we're watching that as well as watching the power with Voyager. 4 watts less per year. So you have to think, what do we turn off next?
And I remember it was just a few years ago that you guys fired the thrusters for the first time in forever. And I guess I hadn't been thinking about it, but I was astonished that they were able to budget that maneuvering fuel for 46 years, where at the time, 43 years. It's like, okay, you got to save at least, 200 pounds or however much fuel is left. I mean, how do you do that?
I don't think the intent was to save any fuel. They just had big tanks and not knowing exactly how much fuel it would take for the flybys. And I think that they could optimize based on the amount of mass they could launch at the time. And when we do the curves to see how long will the fuel last, it's going to far outlast anything else for the spacecraft. So we have plenty of fuel. I don't think that'll be something we'll run out of, unlike Cassini, who ended its mission as we were getting low on fuel.
I was going to say 15 billion miles on one tank of gas is pretty good fuel efficiency. Looking back on the mission from those early days and then coming back to the mission as you did, Linda, I'm curious if there is one or a few of like the key Voyager moments that are your favorites, your standouts, right? You mentioned volcanoes on Io, which I'm very proud of because I believe it was a USC student that played a pretty big role in the discovery there. Rod, right? So,
always pushing for the alma mater. That's okay. But some of us don't have to.
But I'm curious to you, as someone so close to the science, what those moments might be. So when it does come time, let's hope that it's not for many years to come, to turn the lights out. That'll be like, I was really glad I was there for that moment, or that Voyager one was able to do this shock. Obviously, leaving the solar system is a big milestone in itself, but I'm curious if there was something else or more personal to you as a scientist that you're going to take away at mission's end there.
Right. Well, certainly for me, as using Saturn ring data from my thesis to just see the beauty of the rings and see how much detailed structure there was. And then to be part of an experiment that could, at that time, watch the star move behind the rings and measure resolution in the rings down to 100 meters. I mean, that was just unprecedented, much higher resolution you could see in the pictures, and how much we could learn about the waves in the rings and their structures. So certainly being part of that experiment, watching the data physically come to the ground, and going on to use that as part of my PhD thesis is a very memorable moment. And I think another one for me is Neptune's moon Triton. Here's a captured moon in a retrograde orbit so far from the sun. And I remember it was, of course, in the middle of the night. It seems like some of the best data always comes back in the middle of the night. Right. And watching and seeing the cantaloupe terrain there on Triton, and then finally the detection. I think Larry Soderblom put the pieces together to see the geysers coming out on Triton, active geysers at the time of the Voyager flyby, and it was just amazing to see a world, volcanoes on Io and now geysers on Triton. And of course, Voyager also found an E-ring sharing the orbit with Enceladus, and that was our first clue that somehow those tiny particles were getting into space and they were coming from Enceladus because the ring was thickest there, and another world with active geysers going off. So that was one of the breadcrumbs, I think, that Voyager left for Cassini to go back and study Enceladus.
And well, it's one of my favorite moons. We call it enchiladas here in my household. It's the tastiest of the moons.
Moving on.
No, is there one instrument, if you were given a blank check to design and build Voyager 3 right now, is there one instrument that you would want on that for sure to either revisit these planets or do something else in the outer solar system that you've learned from Voyager 1 and 2?
We have so many very capable instruments now with the new technology. And so I think I'd try and get a camera across with a spectrometer, so you could not only get those beautiful detailed images for context, but also, can think of it as a cube. You can get spectra at multiple wavelengths, maybe UV through infrared, to really tell you something about the composition and what's going on with these various worlds. And then, of course, just a very capable, particle and fields detector. You can wrap up so much in a single technology these days to not only explore remote sensing, but in situ around the spacecraft as well. Of course, carrying a few probes, you could decide, I want to send a probe here, a probe there. That would be nice to have too.
So Tarek, you sort of stole a little bit of my thunder, but I guess I'll expand my last question here a bit. So Linda, if you could, let's just say in a year, somebody came to you and said, hey, we want you to write your own outer solar system decadal survey statement for, the 2030s or something. So looking out 15, 20 years, do you have a wish list for what you'd like to see happen in robotic exploration, especially in the outer solar system?
For the outer solar system, I think trying to understand the two ice giants, Uranus and Neptune, would be at the top of my list. We visited the gas giants. We know a lot about them, but the ice giants are smaller and quite different. And of course, they have incredible moons and ring systems of their own. And so they're, systems in their own right. So I would put that high on my list. And then just as a ring scientist, there are some other interesting worlds, tiny worlds that have rings around them. And to maybe visit one of those and try and understand the physics behind what's keeping those rings in place and how they might be working. And of course, there's Pluto. We've had, the New Horizons visit by Pluto. Just saw one side of Pluto. So it might be interesting to go back and sort of complete that picture and look at Pluto as well.
So for planets like that, is it worth going through the expense and mass of an orbiter, or do you just keep doing flybys with better and better equipment?
Well, Pluto since Pluto and Charon, that has an interesting system and interaction between the two. And it would really be nice, if you could really launch spacecraft with big fuel tanks. Maybe you go and you orbit Pluto for a while, and then you find another Kuiper Belt object, and maybe you go off and orbit that or visit some other Kuiper Belt objects, as long as you're out there that far away. Kind of part of what New Horizons was able to do in visiting, objects beyond Pluto as well.
Well, I'm so glad they were able to continue that mission. It was.
I agree. I mean, now they're in that space headed toward the heliopause. I think they probably won't make it to the heliopause, but hey, if they get a really long mission, they might make it too.
Well, this has been an incredible pleasure and a gift to us. So I want to thank you for joining us. This has been episode 110 of This Week in Space, the rescue of Voyager 1. Don't forget to check out jpl.nasa.gov for everything you want to know about Jet Propulsion Laboratory. And there is also a Where is Voyager site that you'll be able to find. We have that listed on the show notes. And of course, don't forget to look at space.com, the website's the name, and the National Space Society at nss.org. Linda, of the websites I've mentioned, I'm sure you know some other place you'd like to direct us to stay current with all this stuff.
Oh, I think you've done a good job listing all of the websites. I mean, NASA has a website too that sort of wraps up all the missions that it's flying.
Okay, I'll make sure I put those in the show notes. Tarek, where can we find your new illustrious history as a gaming master?
Well, you can find me marveling still at. Is that a video game? What is that?
Phone.
That's a phone ring.
I thought they were making fun of me. Linda.
I forgot to turn it off. Sorry about that.
That was perfect.
There,
I thought that John in the back room was making fun of me. No. Well, you can see me marveling at the folks at JPL daring mighty things since 1958, Rod. But no, this weekend I'll be honoring my mother because it's Mother's Day, right? And my wife. So for sure. And at space.com, watching all the things. We didn't, hopefully when we talk next week, we'll be closer to a Boeing launch than we were this week. And we'll be tracking that as well. And on the Twitter, at Tarek J. Malik, or on YouTube at Spacetron Plays, as always. So,
can I just say one word about next week that you've heard me say a few times?
What?
Valves. Okay. Sorry. Right. And of course, you can find me at pilebooks.com or at astromagazine.com, whatever fits your preferences. And Tarek, thanks for reminding me about Mother's Day because I forgot.
Yeah.
And on the other hand, please don't you forget to drop us a line at twis@twit.tv. That's TWIS@twit.tv. We always welcome your comments, suggestions, ideas, and I answer all the emails. So fear not. New episodes published every Friday on your favorite podcatcher. So make sure to subscribe, tell your friends, and give us reviews. We'll take whatever you want, but whatever it is, make sure there's 5 of them at least. And you can head to our website at twit.tv/twis. Please also don't forget, you can get all the great programming with video streams on the Twit network ad-free on Club Twit, as well as some extras that are only found there, including, I think, maybe still Tarek falling out of his chair, which I will never let him forget.
And it'll never happen again.
$7 a month. Yeah, we'll see about that. You've heard Leo talk about what's happening in the podcasting realm, and every little bit helps. So please don't be shy. Step up, be counted. Give us your $7 a month. You can follow the Twit Tech Podcast Network at Twit on Twitter, and on Facebook, and twit.tv on Instagram. Everybody, thank you very much. This has been a really special episode. And again, thank you, Linda, and we'll see you all next time.